All right, welcome. How exciting is this? So I'm going to take my mask down for just a brief moment. I'm not going to breathe, just to show you my face so you can all recognize me. All right. Hopefully the video police don't get mad at that one. I'm Michael Hipfner. I have been a faculty member here. This is my 8th year, I think, as you can tell by all my gray hairs. I'm also the director of graduate studies, so I have been in communication with, I think, basically everyone here at some point. This is Graduate Thermodynamics, and we are either fortunate or unfortunate to be one of the about 20 to 30% of the classes that are going to be in person this semester. So, what that basically means is they did a survey of all the classrooms, and they determined based on the class sizes which rooms would be large enough as to necessitate appropriate social distancing. No classes, I think, can have more than 50 people, but they want to try and keep it under 20. So that's why we are in this, let's say, a classic building. I don't mind it. I like teaching on chalkboards, so I'm excited. So I got to, over the summer, they call this like the Rolls Royce of chalk. So I get to do an official review for a semester to see if it's actually good stuff. So as a brief, I guess, just kind of going over the class a bit, before we go through the syllabus, I wanted to cover kind of what we will be dealing with. So in this class, we cover, it's sort of a hybrid where the first half will be covering more or less a really condensed but in-depth overview of classical thermodynamics. So basically that class that most people just try and survive through, we're going to go back and rederive everything. So today, after the syllabus, we're going to be talking about the history of the first law of thermodynamics, how it relates to atomic theory, and sort of why thermodynamics is set up the way that it is. Then for tomorrow or next class, we'll talk about the second law of thermodynamics and the history of the second law of thermodynamics and why the way that it is. And then for about the next week or two, we'll basically cover everything in a first semester thermodynamics class. Energy balances, entropy balances. I'm basically going to assume you've already seen these before, and then we'll jump into the detail. But the meat of it will be in phase equilibrium and how we use an equation of state to perform phase equilibrium calculations. Then, so for the second half, or this, maybe it's more like a third of the class, we'll talk about statistical mechanics. And this is really where previous scientists have use the concept of atomic theory and the concept of an atom or a molecule to justify with thermodynamics. So part of the confusion, I think, in thermodynamics is more or less because it seems arbitrary and abstract, and that's because it was arbitrary and abstract when it was formulated. So the key thing to keep in mind for thermodynamics is that what we are teaching is not really the answer or the only answer. We're teaching the system. So I think of thermodynamics as a system that people agreed upon hundreds of years ago as the best way to organize data and perform advanced calculations. So that's why some of it seems a little bit arbitrary. That's because when it was formulated, it was arbitrary. So this book here is the one that I do recommend. This is for the second part. It's Sandler's Introduction to Statistical Thermodynamics, which is listed here in the syllabus. So if you guys go to the Canvas website, this is accessible under the Files tab. Then the other book, for the first part of the class, this is the one that I use. This is, again, Sandler's book. I always joke that he owes me a Christmas gift because I have 2 of his textbooks for the course. I don't expect you to necessarily buy this book. If you have a good undergraduate chemical engineering thermodynamics textbook, you'll probably be A-okay. So something like Smith, Van Ness, and Abbott is a really classic one. This one I very much like because it is big, comprehensive, thorough, detailed, with lots of really excellent tables that basically organize how to perform thermodynamics. And it breaks it down in sort of a very similar formulaic way to how I teach the class. So that's one I like, but I will not be assigning any problems out of the textbook. So this book is really just for your reference. Everything you need to know will be included in the videos, and the homework problems will be comprehensive in themselves. So you don't need it, so I'm not going to say solve problem 2.7. I'm not going to do that. If I do, I'll transcribe it and then kind of put my own twist on it to make it unique. So you don't need to worry about the edition. There's a 5th edition. This is the 4th edition. They're basically identical. The only difference is the 5th edition has new problems, which isn't going to make much of a difference because I'll just transcribe any problems that I put out in the book. Okay. Next up, let's go to the Canvas page really quickly. So this is the class Canvas page. I kind of keep it a little bit bare bones. Most everything that I put, hopefully you guys can see this, most everything that I put, I do in the Files section down here. So for example, this right here is the syllabus. Any sort of papers that I think are really thought-provoking or interesting, I will have them here in this literature. And then the resources, this is going to be equation sheets and summary files that I've created over the years that I would really recommend you go through, save them to your own personal computer because they're really helpful resources in the future. The most important one is this one here that I have been refining for over the course of maybe, gosh, I don't know, too long. Maybe about 10 years I've been refining this file, and it's completely blank. Let's see, where is it? There you go. So this sheet right here is basically the entire class. We have open system energy, open system entropy, definition of PV work. We have ideal gas relationships. We have material properties that are defined, for example, heat capacities, thermal expansion, isothermal compressibility, some equations of state. This right here is sort of the horror section, I think, of most people's undergraduate chemical engineering classes. This is your differential relationships between different thermodynamic variables, Maxwell relations, definitions of fugacity for mixtures and fluid phase equilibrium. This is where we're going to be spending a tremendous amount of our class. More multi-component stuff, and at the end here we have some statistical mechanics relationships as well. So this is one that I personally refer to, I would say very frequently, at least once a month for my research purposes. This is what I'll take a look at. Then if we go on the home page, I have links. I'm going to add a link to the fall 2020 video lectures. So just as an example, it'll take us back to good old times without masks. This is a playlist. Basically, every single class is already there. Now, I don't make any guarantees or assurances about the quality of the video, right? So what I do is I shoot it on the iPad, and what that just allows me to do is trim the ends, upload to YouTube. So basically, within an hour, the lectures will be available online. And that gets us to some COVID concerns. So let's talk about those before we go into more detail. So I'll go back and we'll talk about how the class is being run. But I wanted to talk about COVID because apparently that's all we can talk about. This is boilerplate language from the University of Utah. So don't think that I sat down last night getting really in a huff and then sort of writing a big long rant about face masks. The University of Utah bolded this last one, so I bolded this last one too, right? So face shields are not acceptable unless you're wearing a cloth covering as well. Everyone's wearing a mask, so not a big deal. I will try and bring hand sanitizer just in case the stations don't work. I will bring extra masks in case something happens. So I hopefully will be a resource to make this go smoothly. Again, all of these are these are University of Utah boilerplate stuff. So again, I did not go on a long rant about COVID last night. All right, you're encouraged to wash your hands, use hand sanitizer, clean your desk area with wipes, and they say that'll be available at classroom entrances. I hope that is stocked and maintained. But your guess is as good as mine as to how well this is going to go for the whole time. It's university policy that the instructor can more or less determine whether or not in-class attendance is mandatory. So for example, that would be the case for a lab class, right? If you're expected to do an experiment, you kind of have to be there. This is not the case for this particular course. So for today, I didn't necessarily spend out an email, but I do strongly recommend in-class attendance, and this is my edition, the rest of it is university policy, right? But if anyone, for any reason, feels uncomfortable, if you feel unwell, particularly if you suspect that you may have had an exposure, then you are basically allowed to participate online rather than in person. So to facilitate that, I will be recording all of the videos. If, for example, something goes wrong, you have a generation's worth of old lectures that you can go through the information won't be 100% relevant in terms of when a homework is due or so on and so forth, but it will be present for, kind of as a resource. But I will try my best to make sure that every video doesn't get destroyed, but sometimes the iPad has issues. Any questions about that? Or any questions about COVID at all? Okay. If you do test positive for COVID, you must report it to the University of Utah. As far as I know, there is absolutely no retribution whatsoever. Right? So it's more important that we know what's going on than it is to get mad at people and punish them. And then a last note here is that this semester is going to be a little bit odd. So we originally had we still have a vice presidential debate scheduled for October 7th. So that week, they are going to go online in order to, I guess, free up space for media types and things like that, and I'm assuming make a little money on the side. And what they decided to do is that the week before that, so the week of September 28th, to go online as well. And so what this kind of gives us is a baked-in 2-week quarantine in the middle of the semester to basically regain control if anything goes out of control. And then lastly, the time period here, November 30th to December 3rd, this is the time period after Thanksgiving, because we don't have a fall break, but since most of you are new students, you didn't know about the fall break, so no real loss on that part. Fall break was nice. It was a week off in the middle of the fall semester, but they end the semester a week earlier because we're not having that break, and so really it's only 2 days after Thanksgiving. It really doesn't make a point to bring everyone back, especially if you're going home to see your families and whatnot. So that will also be online. The plan is I will plan on teaching it on what they call synchronous lecturing. So that means that I will be live on Zoom, and you guys can all join live on Zoom as well, and I will be recording it. So it'll be a slightly different format, but just based on my previous work with recording videos, I'm not particularly concerned one way or the other. For the online stuff, if the university does shut down, the plan will basically to be continue on the schedule as usual, except for quizzes and projects and homeworks. Everyone will just be expected to take like a photo of their exam and upload it as a PDF to Canvas, and I'll grade them that way. Okay. Really fun policy discussions today. Before I forget, so the TA for the semester is Brennan Shanks. He is back there in the corner. I am not going to necessarily expect that he attends every lecture. He was in my class last year. He's also a PhD student in my research group. I can attest that he is quite good at thermodynamics, but he will be available for set times for office hours. I'm planning on holding the office hours by Zoom for now, but we'll see how it goes. If we can find a nice shaded park bench or something like that, that might be an acceptable substitute in the future. I don't really know what the culture and the policy is going to be for in-office meetings, right? We're all kind of learning this on the fly as it goes. But thank you all for showing up today. I appreciate that. Okay, let's see. You can read through the course objectives. Basically, they're just they're written in a form of an action or an activity, things that I would expect you to be able to do, like use an equation of state to solve phase equilibrium and so on and so forth. The homework, I expect basically you guys to do it on your own. So every homework assignment has to be submitted individually, but I'm kind of expecting that we get value added by people working together in groups. Just please make sure that you work, your final assignment is on your own, you submit it on your own, and so on and so forth. All homework will be submitted by Canvas electronically, so I don't really think there's hardly going to be any papers exchanged except for in-class quizzes, assuming we can survive through the semester until we can have those. I accept late homework up to 1 week late at a 50% penalty, so I don't really think that the scores of the homework are worth it, but I really think the knowledge contained in the homework is really where you want to be spending your efforts. Now, for how the class is going to be run, because there's a very high likelihood that if we have an uncontrolled COVID outbreak on campus, we're going to be shifting to online only, then I would suppose that this class would be one that's going to get the axe because there isn't a lab component. So if push comes to shove and people do go online, I'm willing to bet that our class would be one of those that would fall that fate. So what I've done, and this is suggestions from other faculty across the country, is that in order to mitigate any concerns of academic misconduct, is to sort of spread out the course effort over the course of the entire semester and not have like a final exam that's worth 50% of the course that, you know, highly incentivizes a couple of people to cheat. So instead, we're going to have no exams. I'm going to call them quizzes, right? So the homework is going to be 15%. There's going to be 6 or 7 homework assignments, maybe a bit more, just because the format's a bit different, but there's flexibility there. And then we're going to have a series of 4 quizzes that are each going to be sort of a length that can be reasonably easily completed within a course. My traditional way of doing lecture or exams is to basically slam as much on the exam as possible, so time efficiency is really key. So you got to crank out, you know, a lot in an hour long. But I will try my best to make sure that these 4 quizzes, because they're a bit more frequent, are a little bit less time consuming. And so those would be administered in person on the schedule. But if we do go to an online format, you would work on them on your own, and you would have to submit them to Canvas by a pretty firm deadline. So it would be, I would send the email out at the same time that everyone gets it, and then, you know, start working on it and send it back. Here's a section on academic misconduct. I think everyone knows exactly what that constitutes, so please don't do that. Grading here, this is kind of like the harshest I'm going to be, but I have the leeway to drop it down to not, you know, make everyone panic. Let's see, a couple other notes. So regrading, if you do feel like I made a mistake on grading, then all I ask is that you submit in writing within 1 week from the time it was handed back what the perceived error was. And in that policy, you also have to demonstrate that you understand the problem. So basically, to raise the barrier of entry, just not come up and say, hey, Michael, can you regrade everything? And I would say, oh, it's perfect. Here you go. All right, so be very explicit. This little write-up is your voice in the room when I look at all the regrades. And it's sort of you being there saying, hey, this is, I know this stuff. All I did was I put a -R instead of a +R, for example. Okay. This is boilerplate university stuff here, but I wanted to make a really quick comment on this one right here, the students with disabilities. We do have a Center for Disability Services. I have no idea how it's going to be operating this semester, but in general, if you have any sort of a barrier to sort of performing well in the course through some sort of a learning disability issue, they can make accommodations. It could be quiet testing room, it could be time and a half, it could be double time. I always encourage students, if you have any challenge, whether, you know, diagnosed or undiagnosed, go talk to them, because I want this to be sort of a fair fight for everyone, and I just want to reiterate every semester that no faculty sort of look down on this approach. So I don't want people to feel like, oh, well, I don't want there to be any perception that I'm cheating the system. No. We want it to be fair. We want everyone to learn. If there's something that we can do to help you out better, please do reach out. And then we have a couple of statements on safety and sexual misconduct as well. But again, boilerplate university stuff. We covered the COVID. And then the class schedule. So this week we'll be talking about Introduction to Thermodynamics. Then we'll move into basically the Maxwell relation type stuff, phase equilibrium, and then a quiz that kind of will encompass more or less energy and entropy balances, like the Rankine cycle, the Carnot cycle. You know, how much energy does it take to heat up a lake and things like that? What's the delta H if you assume a constant heat capacity versus a not constant? We'll then shift online for a little bit as we talk about phase equilibrium. Quiz 2 is going to be focused much more so on phase equilibrium. Vapor-liquid equilibrium, liquid-liquid equilibrium, using equations of state for state changes and things like that. Quiz 3, we'll also talk about phase equilibrium and a little bit of statistical mechanics. And then finally, in the final exam spot, we're going to be sliding in quiz 4. So this one, of course, will have to be online. And that one will be a little bit more or less comprehensive. 2 things I forgot to talk about are the projects. So we're going to have 2 projects. One of them is going to be excuse me, I'm not quite sure which is going to be the 10% and the 15%, but one is going to be more of a phase equilibrium calculation. So for example, I'll say use the Peng-Robinson equation of state, use it with your own code to do a PT diagram for a non-ideal mixture, right, for example. The second project will be a little bit more of a bridge between classical and statistical thermodynamics, calculating something called a Kirkwood-Buff integral. This is something that is very rarely, if ever, talked about in undergraduate courses, and very rarely, if ever, talked about in graduate level courses. But it is a focus of one of a major research project in my group, one of which Brennan is actually working on. And this is to use neutron scattering to measure fluid structure. And then the Kirkwood-Buff integral is a way that you can actually determine how molecules are locally oriented to macroscopic fluid properties, right? What is its density? What is its heat of vaporization? Things like that. So the Kirkwood-Buff integral is a really good bridge between those two. And as part of the grant, you guys all get to help participate by basically helping to build up a library of different Kirkwood-Buff integrals that can be used for the research project. So if you don't like that idea, you should blame the NSF for funding the project because this is part of the teaching and research integration work of that grant. I am about out of things to say about the flow of the course. Do we have any questions? So if you do have concerns about COVID, you don't like the in-person format, you feel nervous or anxiety, let me know, right? I don't expect you guys to raise your hand right now and single yourself out, but please let me know and I'll try and find a way that we can work for accommodations. One other final note, I'll give it a little bit to settle down, but the university is recommending that we have a seating chart. The purpose for that is for contact tracing. So if you like where you're sitting, that could be your seating chart position, or we can wait sort of more or less a week or so to, I don't know, make your friends and find the perfectly comfortable chair, for example. And then if that's the case, then we can kind of lock that in for the rest of the semester. So in the unlikely or in the event that we have someone who does test positive for COVID, then we can basically let people know, hey, this is where they were sitting in the next class and so on and so forth. So as a courtesy to the university and subsequent people who use the classroom, I think it's a good idea to enact. All right. So I am originally from Salt Lake City, technically Cottonwood Heights. So those of you from the area, I went to Brighton High School down in the southern part of the valley. I did my undergraduate here at the University of Utah. Then I did my PhD at the University of Michigan. I worked with Scott Fogler. He's the guy that wrote the kinetics textbook, but I did not do any kinetics with him whatsoever. I very much avoided teaching the class with him because he was a taskmaster with his graduate students or TAs that were helping him out on that. So for those of you who are unsure of your research interests, I was unsure of my research interests when I went to graduate school. Right? I ended up working with Scott Fogler on oil and gas, specifically heavy hydrocarbons called asphaltenes. And so the challenging part about asphaltenes is really what inspired me to work a little bit more in depth in thermodynamics, is that in thermodynamics, we have sort of limiting cases. One limiting case is the ideal gas. In an ideal gas, it's a single isolated molecule whose properties are only predicted for one individual compound. Now, the real challenge of thermodynamics for a real application is that when you put molecules into a dense mixture, like a liquid or a solid, we talk mostly about liquids as chemical engineers, really everything comes down to one simple thing. That is, what is the relative orientation of molecules to their neighbors? And that determines all thermodynamic properties. And statistical mechanics is the link between this is a molecule, this is how it behaves, these are the properties that are going to come out of it. Now, in oil and gas, equations of state are exceptionally common and prolific, particularly for reservoir engineering. Now, in an oil reservoir, you can have tons of cubic kilometers of rock with oil flowing through it. And what they need to be able to know is at a particular temperature and pressure down in that rock, what is the phase of matter, right? Is it liquid? Is it a gas? Or what is the composition of that liquid so you can predict what its viscosity is, for example. Now, the challenge is that for simple molecules, your normal alkanes, we have something that is extremely well optimized. For example, the Peng-Robinson equation of state was designed in the late 60s and the 70s to be used for reservoir modeling and distillation of oil and gas subfractions. It is optimized to predict those properties, and it does it quite well. But it does it from the vapor side approach. It doesn't predict the liquid properties particularly well. Now, asphaltenes are the bottom of the barrel, right? They don't have any boiling point. They don't volatilize. They'll actually thermally decompose before they actually turn into a vapor. And what's nice about those compounds is that they're really, really challenging, and that they stack as like coin discs. Right? They're these big polyaromatic hydrocarbons that stack. And so the novel thing about them is that what makes them so hard to model is that the local fluid structure is so massively perturbed from even a simple liquid like a normal alkane, and even more massively perturbed from something like an ideal gas. So my inability to understand asphaltenes has sort of inspired our work to go to even a more fundamental level. And what my research group does now is sort of span that gap from applied oil and gas research with a particular emphasis on heavy hydrocarbons, their self-assembly, how those self-assembling molecules relate to organic semiconductors that are used in, let's say, OLED TVs or organic photovoltaic solar cells. Right? The same problems that the oil and gas industry is experiencing in understanding how these hydrocarbons interact is exactly the same problem that people in the next generation of organic electronic devices are struggling with as well. So that means that there was a scientific gap that was unexplored. So what we're also doing is on the far extreme other side is that we are looking at simple fluid structure. So we use neutron scattering. So we'll go to a facility in the UK called ISIS, which is unfortunately poorly named, but in the term of COVID, I haven't heard the word ISIS in basically forever. It was named in the 80s, but I'm sure they've heard all the jokes. And I also go to Oak Ridge National Lab down in Tennessee to do neutron scattering. And so what you do is it's a relatively simple experiment. You shoot neutrons at a liquid. The neutrons are so cold that they behave like waves. They're around 3 to 5 Kelvin, right? So they actually have a wavelength of a couple of angstroms. When those neutrons hit the nuclei, they scatter out. And the pattern that they scatter in tells you where the molecules are located. Neutron scattering is more powerful than something like X-ray scattering, right? X-ray scattering is what they used to discover the structure of DNA. It was very first used by the Braggs in the early 1900s to determine the crystalline structures of simple molecules. Because X-rays interact with the electrons. I can't change how an electron behaves. But with neutron scattering, I can swap out hydrogen for deuterium, right, which is just a different isotope, and then deuterium scatters vastly different than hydrogen. So what we can do in our group is if we shoot neutrons at a liquid sample of, let's say, benzene that's fully hydrogenated versus benzene that's fully deuterated versus a blend of those, I can highlight different regions of the molecule and I can deduce the disordered structure of it. Now with that information, the goal then is how can we use measurements of local fluid structure to better understand, validate, and improve either quantum mechanics predictions, statistical mechanics predictions, molecular simulation approaches, and then ultimately how can we apply that to solve engineering problems of maybe, for example, designing molecules for self-assembly, better predicting oil behavior, right? Better choosing solvents to process some sort of a solution processable device. So that's the type of work that we do, and so I'm very fortunate to be teaching the graduate level thermodynamics course where we can bring in a lot of the research discussions that is not really feasible in an undergraduate setting. So that's a little bit about me. Following up, I guess, on what I mentioned before, when I started in graduate school, I had no idea what I wanted to do. But the good news is that I think if you approach research from just sort of an innate curiosity, you will never be disappointed. Because regardless of the type of project that you're working in, right, it may seem vastly different to start on an oil project. And you might want to think, oh my goodness, I'm going to be pigeonholed to work for the oil industry for the rest of my life. But if you identify the scientific gaps, then essentially, if you identify what those are, then you can more or less apply those to the gaps in any different field. Right? So I worked very closely with ExxonMobil the past couple of years. And one of the things that was really hopeful is that they have some of the best researchers in the world. Right? ExxonMobil will have people that go from industry to academia and back and forth. Right? That's very uncommon with a lot of industrial research labs now because they don't publish as much, they don't do fundamental research, so it's hard to make a transition back to the university. But I knew that they had a lot of money, they were willing to spend the money on research, and that they still didn't have the answers to the questions. And I know they were not bad researchers. They had access to all the physics literature, they had access to all the chemistry literature, and they still didn't know how to solve the problems. And that basically gave me the power to say, hey, they don't know what's going on. There's some real scientific questions that are unanswered here, and that's a tremendous opportunity. So regardless of what fields that you're in, if you're working in bio with cells versus neutrons versus simulations, really, a day-to-day basis, graduate research is more or less the same, right? You're in the lab, you're pouring one chemical into another chemical, you're taking that sample and you're putting it into a machine. Now, which chemicals you mix and which machine you use basically dictates the field of study. But the approach of good thinking, good research is universal. So I wouldn't be too worried about necessarily finding a project that 110% fits your interest because it's much more transferable than you may think. It's really the nomenclature that you're committing for when you do a particular field of study, right? You have to build a reputation in that area, you have to go to the conferences, you have to meet people, and so on and so forth. So just a word of advice for those of you who are looking for research projects. All right. So let's get into actual thermodynamics. And I don't think we'll be able to cover the first law, unfortunately, today, but I will talk about the introduction to thermodynamics, which I think is a way that is not really taught in undergraduate courses. But to me, it's sort of the only way to think about that. And I will start off. The chalk is nice, but it's not like spectacularly nice. I'm a little disappointed. Okay, so thermodynamics is the study of how heat and energy is stored, okay? And how it is transferred between different ways of storing that energy. But in order to understand classical thermodynamics, I mean really understand it, they say, well, you have to teach it, but I'm going to try my best to describe thermodynamics from the most fundamental perspective. Thermo only has 3 variables, okay? U, typically, we'll write everything in intensive units, joules per mole, and then my notation is an underline to remind us that it's an intensive unit, right? So for example, U is internal energy in units of joules, U underbar is joules per mole. But I will promise you I will slip up on my nomenclature at some point. But just know that you must have dimensional homogeneity. You can't add joules to joules per mole. Right? So if I don't specify, you can usually deduce what it is. Now, internal energy is frustrating. What is internal energy? This is a question for the class. Anyone want to be brave? What is internal energy?
It's like the energy involved in a bond formation, like the chemical energy involved in a bond itself.
If that's part of it, yes. What else can internal energy be? So we have bond energy is a form of internal energy. What else do we have?
Vibrational or rotational of molecules.
Yep. What else? There's one more. One more big one. There's lots of other ones, but one more big one. Translational energy, the kinetic energy of the molecules themselves. So the key thing that we have to remember, internal energy, thermodynamics, Carnot cycle, industrial revolution, all of these events happened before we knew what an atom was. When I give, for example, my hand sanitizer bottle here, if I were to give it 100 joules worth of energy or 100 kilojoules worth of energy, I don't get to tell it what it does. I give it 100 kilojoules worth of energy, and it decides what it wants to do. Does it want to have more translations? Does it want to have more vibrations? Does it want to have more rotations? Does it want to have a chemical reaction? Does it want to volatilize? I don't get to choose what it does. So back in the early days of thermodynamics, no one cared, right? They didn't know it was a bunch of ethanol and water molecules with some sort of viscifier, right? It was just a fluid, and you gave it energy, and it did something with the energy, right? So you have to keep in mind that when we start this class and we do classical thermodynamics, we don't know what an atom is. Everything in classical thermodynamics is independent from the existence of atomic theory. It is entirely accurate and self-consistent. So every time you get confused in thermodynamics and say, hey, why is it like this? Why is it arbitrary? Remember, I don't know what an atom is. So when atomic theory was sort of produced in the late 1800s and early 1900s, right, very hard to believe that we didn't know what it was until basically 100, 120 years ago. Statistical mechanics was the theory to unify the concept of an atom with the well-established predictions of internal energy, energy balances, entropy balances of classical thermodynamics that had basically built all of the ships, all of the factories, every battleship, every tank, every engine in the world up until that point, right? So people knew how to manipulate fluid properties already. They didn't need the concept of a molecule, right, to build aircraft carriers. It helped. Then quantum mechanics came very quickly after in about the 1920s, 1930s, and 1940s, and still to this day we're working on it. Quantum mechanics had then had to justify with not only classical thermodynamics, but also statistical mechanics. So every time we get confused about thermo, remember, translate yourself back into a time when that, molecules and atoms didn't exist, right? And that'll help sort of give you confidence that no one knows what's going on. It's not just you. And since thermodynamics has been around for so long, basically, we have built up a very well-established system. So, I'll stop rambling and kind of get through at least the introduction before today's over. Variable number 1, internal energy. Variable number 2, anyone want to hazard a guess what this one is? Entropy. We could fill a whole class. We could fill a whole lecture, a whole semester with entropy discussion. We'll talk a lot about entropy today. This course. Internal energy, not that hard, right? I can assure almost everyone here can do energy balances. Entropy is what we'll be spending most of the time in our class because it actually is by far the more interesting of the factors. The third variable of classical thermodynamics, by which the universe is defined, is density. Now, I always say density, but I write it as V, its specific volume, right? So this is going to be cubic meters per mole. So then the density is just going to be equal to 1 over the specific volume, which is then going to be, in terms of molar quantities, moles per cubic meter. And this is it. 100% of thermodynamics is built upon the interaction between these three variables. So in its most basic form, thermodynamics is the derivation of the relationships between these three variables. As a general sense, equation 1 would be the first law. Equation 2 would be the second law. And equation 3 is what we are doing in thermodynamics. So in classical thermodynamics, everything that we're doing is to develop this third relationship. And most generally, this comes in the form of an equation of state. For example, the ideal gas law, the Peng-Robinson equation of state, the Saft equation of state, which is a relatively modern one. So the first law, we can generally write as the change in internal energy is equal to the heat input plus the work input. Now I write du as a differential, but I write delta Q and delta W. The reason for that is that U is a state function. It is only a function of what your current conditions are. Temperature, pressure, volume, whatever the case is. It doesn't matter how you got there, that's the internal energy of the fluid. So when I give this hand sanitizer enough energy to be at a given temperature and pressure, its properties are always going to be fixed because the molecules have a mind of their own. They get to determine how they store their energy. So that means I can write that delta U is equal to the integration of the differential form of the internal energy. So one of the challenges of thermodynamics is that we don't actually have any relationships to directly predict the properties of our thermodynamic variables. We can only predict the rate of change of the thermodynamic variables. We know how much the internal energy changes when I put energy into it, but I can't tell you the absolute value. So for example, I can't tell you how much energy is in this bottle. Because what energy are we talking about? Do we want to include the energy in the chemical bonds? Do we want to include the energy of the electrons? Do we want to include the energy of the neutrons if you explode them? Right? So it's all arbitrary. So all we care about is the rate of change. Excuse me. The second law is really quite simple. Oops. That's right. S is greater than or equal to 0. That's it. Entropy increases. Now, oftentimes you'll see it written like this: ds is equal to right. That's a very common way to look at the second law of thermodynamics. But here's the problem. U, S, and V. Those are the only variables of thermodynamics. What is this? Does not belong in a fundamental form of the second law of thermodynamics because you're relying on the existence and the interpretation of temperature. Another critical factor is that entropy, see, don't screw this up, must be concave. That regardless of which property I vary, entropy must always look like this. It can never look like that. The function, so this is no good. So this is any function x. This could be a reaction coordinate, this could be temperature, this could be pressure, this could be density, it could be anything. Entropy must always be a concave function. And that's sort of a critical asset of what allows thermodynamics to be performed. The issue here is that entropy is maximized at equilibrium. And if I were to have a function that is convex, equilibrium is established when no variables are changing. So ds, du, dv, everything is 0 at equilibrium. The only way that this is possible is right there. And that's what we call an unstable equilibrium. Because any small perturbation, right, will cause the entropy to increase, and again, the whole universe will explode out uncontrollably. So it is a critical stability criteria of entropy that it must be concave, meaning that equilibrium is a stable equilibrium. And it's sort of a mathematical consequence of this. So, in classical thermodynamics, there is no good understanding of what temperature and pressure are. It took until Ludwig Boltzmann, right, to design, well, Maxwell as well, sorry, to design statistical mechanics and atomic theory before we had any physical intuition of what temperature and pressure were. Temperature, defined classically, is the relationship between entropy and internal energy at constant volume. It says, at a constant density of my fluid, how much does the entropy change when I change the internal energy? That is the classical definition of temperature. Likewise, pressure is defined, right? It's a defined variable, is the relationship between internal energy and volume at constant entropy. So then if we put everything together, for example, in the ideal gas law, what we see here is that we have 1, 2, 3, 4, 5 variables. 5 unknowns. We have U, S, V, T, and P. So we need 5 equations. We have the first law of thermodynamics. We have the second law of thermodynamics. We have the definition of the temperature. We have the definition of the pressure. And we have an equation of state. 5 unknowns, 5 equations. We can solve for all relevant properties of a thermodynamic system. And that is really the foundation of thermodynamics. But the reason why thermo sucks, and it's not particularly pleasant for most students, is because we don't actually have a direct formula that we can just plug into MATLAB, do reduced or echelon form, do some stochastic solver, whatever the case is, right? All we have are the differential forms of how the internal energy change, the differential form of how the entropy changes, a really unpleasant definition using PDEs for how the temperature and pressure relate, and thankfully the equation of state is a nice equation. So really, all of thermodynamics, whether you're talking about chemical engineering thermodynamics, civil engineering thermodynamics, material science thermodynamics, physics thermodynamics, is in which ways do we manipulate these variables such that we can come up with practical solutions based on these systems that we are relevantly interested in. Now, the last thing that I'll talk about is that the variables that every one of us probably spends the most time worrying about in thermodynamics, again, are just made up. Enthalpy is defined as the internal energy plus the pressure volume contribution that is useful for open flowing systems. The Helmholtz free energy is defined as the internal energy minus some lost work term, minus TS, and that the Gibbs free energy, we can write it out here fully, U plus PV minus TS. This is useful for phase equilibrium, and this is useful for open systems. And constant P systems. Right? Something where the system can expand and contract like a balloon versus like a bomb. Right? These are just functions of convenience. We don't need them, but they're very helpful to have and they're very useful. And this is why I really like to stress the point that thermodynamics is the system that we are talking about. It is not the only way to do things, but it is a very useful system, and it's a system that has been improved upon for like 400 years. So if I'm going to choose a system to teach, I will choose the classical system to teach. So I will actually be talking about the history of the first law of thermodynamics on Wednesday, because I was a little bit too long-winded and there was too much excitement associated with these new COVID regulations. So that is all. We are out of time. So just to reiterate, please let me know if you have any concerns, if there's any precautions that you would like me to take to make sure that everyone is having a safe environment in the class. I'm so happy to be teaching people in person. I'm so happy to be out of my house where I share a room with my dog. So I'm glad to be back. But if you are not, please let me know, and I will do my best to accommodate everyone's needs. See you all, actually most of you tomorrow, because I'll be giving the orientation for the new PhD students in Intro to Research. Okay, see ya.